So welcome back to 4.5 of part 2. Example 8, a rotating camera. A camera is mounted 3,000 feet from a rocket's launching pad. The camera needs to pivot as the rocket is launched and needs to keep the rocket in focus. If the rocket is rising vertically at 800 feet per second, how fast is the camera to rocket distance changing when the rocket is 4,000 feet high? So here again, we want to do a couple of things. First, we want to determine, right, well, we're given, you guys have a picture. Now, it says it's vertically rising, so this is our y value right here. And then we want to figure out this right here, right? Let's call that z. So we're given that we have a fixed distance horizontally. It says the camera needs to appear as the rocket launches. If the rocket is rising vertically at 800 feet per second, so that would be dy dt. We know how fast it's going straight up, right? And that's equal to 800 beats per second. And then how fast is a camera to rocket distance changing? So we need to figure out z dt, right? And then, so we need to find, and then find the equation we're going to be using for this, right? In this case, if you guys haven't figured it out, it's already a right triangle. So we need pretty much, we're going to say 3,000 squared plus y squared should be equal to z squared. All right. And then we take the derivative from this. So we're going to, this is pretty much just 0, right? It's a constant. So we get 2y times dy dt equals 2z times z dt. And then from here again, we pretty much figure out the rest of it when the rocket is, so we know y is equal to 4,000 feet, right? If that's 4,000 feet, that means that z has to be equal to 5,000 feet at that moment. So this is going to be 2 times 4,000, right? And then times dy dt, which is 800, equals 2 times 5,000 times dz dt, which is pretty much what we're trying to find. Again, we simplify here. So we have divide both sides by 10,000, right? So in this case is that. So here we're going to end up with pretty much 640 feet per second. And that's going to be our dc dt. So again, the distance, we can say the distance between the camera and the rocket is changing at a rate of 640 feet per second. And then part B says, consider the same problem above. How fast is the angle of elevation of the camera changing at the moment when the rocket is 4,000 feet high? So for this part, we're going to have to use pretty much our, we're trying to figure out the angle, how fast it's changing, which is this right here. So let's call that theta. So again, it's still the same thing. We want to figure out how fast this is changing. So we're given that dy dt equals, again, 800, right? And then we need to find d theta over dt when y equals 4,000 again. And then to do that pretty much, so if you know this is 4,000 and we know this is 3,000, so using again the classic SOHCAHTOA, here we're going to use opposite or adjacent because those are the two values we're given. So we can use tangents of theta, which will be equal to y over 3,000. Or in this case, again, remember, we want to make sure that we substitute the value of y until we take the derivative, right? So that way we don't eliminate it as a variable, as a derivative constant, excuse me. So here we're going to take the derivative of tangent of theta in this case. So that's secant squared of theta times d theta over dt. And that's equal to 1 over 3,000 times dy dt. So secant square of theta would be just 5,000, right? It's just a ratio over 3,000, each term squared. So times d theta over dt equals to 1 over 3,000 times 800. And then we simplify again one more time. Again, don't be afraid to plug everything into your calculator. You're going to find that d theta over dt equals to 12 over 125 radians per second. So we can say that the angle of elevation, is changing at a rate of 12 over 125 radians per second.